Let's look at timing checks. In this module, let's identify what the setup and hold checks imply and how it affects the flops and how information is actually stored in the flops, and then also identify how they actually are stored in the libraries for the SDA tools to actually use to calculate the requirements. A flop or a flip-flop or register as it commonly is known is one of the common storage elements, and it is edge triggered. And if we look at the timing arcs in the flop, you have the D to Q timing arc, and then you also have the clock to Q timing arc. One thing to remember is that in an edge triggered flop, the input data is actually propagated to the output only when the clock triggers the data to actually go from D to Q output. So therefore, all the timing information that is calculated from that clock edge. And when you look at the timing calculations, the clock to Q delay of the clock to Q timing arc is what is used in timing. So SDA tools will actually use that clock to Q delay whenever you look at timing reports and stuff, and the delays are calculated from the clock edge. So the important timing parameters in a flop are basically the clock to Q delay, and we also have the setup time and the hold time requirements, and we'll talk about those in a second. In order for the data to be safely stored inside a flop, the data must be stable for it to trigger the saving of the data into the flop. So basically, if the data is not stable and is changing during that particular setup time, the data is actually not stored in the flop. So basically, setup time can be defined as the duration of time that the input data must be stable before the triggering edge of the clock. So if you look at the graphic or the illustration down below, uh, there is some slow logic, and the data is actually going from Q1 to uh, D2, and basically the data is being transferred from flop 1 to flop 2. And uh, if you look at the D2 signal, the D2 signal is actually changing before it actually before the cycle 2 starts, which is the clock edge where the data actually can be saved into flop 2 is actually uh, the D2 is actually changing even before that. So basically, because of that, the data will not be stored into flop 2. So you have different signals here. Q1 is actually shown, so there is Q1, and so the Q1 data actually takes some time through the slow logic to arrive at D2, and so you have Q1 data from the previous cycle is actually changing before the cycle 2 begins, or the rising edge of cycle 2 for clock is actually changing. So because the new data is already arriving, the data is now currently not going to be saved into the target flop. So what happens when D2 is slow to arrive? Your setup time is obviously violated and the new data is lost. So if you look at the animation, the data from the previous cycle, so as long as the slow logic is too slow for the clock edge to capture the data, then basically the data is lost. the same thing happens when you have a really fast clock. So when you speed up your clock, your setup time is violated because now the data becomes slower compared to your clock, and so therefore the new data is actually lost. So in order for a good functioning circuitry, your clock cannot be too fast compared to your data. In order for your data to actually be safely stored, the other requirement is your hold time. So basically the hold time is the duration that the day input must be stable after the triggering edge of the clock. So the data must be stable, and the data delay must be greater than the hold time of the target flop, plus any clock uncertainty between the flops, so on and so forth. So all of that requires that your data cannot be too fast. Basically, that's what it amounts to. And so therefore, you can correct the hold violations by providing some data to some data delay. And so therefore, you can either uh, decrease your clock uncertainty in the design, or you actually can also add delay cells. So one of the things that people actually do is they try to reduce the amount of skew between the clock trees by using better clock tree generation and so on and so forth. So uh, if you constrain your clock trees properly, there won't be any hold violations because that minimum data delay requirement is now met. So if we look at this illustration, the D2 input is actually switching uh, during when the old data is actually switching and becoming new data, and so therefore during the hold time requirement, and so therefore the data is not captured safely into the flop. So obviously what happens when the data changes immediately, you'll have a hold time violation, and even though it is caught within the edge, the data is actually still lost. This is why the hold checks are actually done at the same edge rather than doing it at the next edge. They are done at the same edge. So basically the setup and hold checks are captured in your libraries, the .libs, in the form of lookup table. And so for a given set of load and skews, these setup values and hold values are actually captured at different conditions of load and skew, and therefore the setup is actually shown as a positive value, and you have to meet that setup check that is provided by that value for those load and skews. And for the hold, the values are actually shown as a negative value, and so both of these have to be met for this particular flop to actually safely save the data into the flop. Take a minute to try this activity. When you have multiple clocks, the capture clock is where, and the capture flop is where you need to actually look at doing your setup checks. So even though there is clock 1 and clock 2 is the one that requires the safe storage of the data into the flop 2 here. So therefore you need to make sure that when the setup checks are actually run, that the setup check is actually happening on flop 2 and not flop 1. Because there are many edges where the launch and capture can actually happen, in the case of multiple clock domains, we do need to look at the most restrictive capture and launch combination. So if we look at the time 0 launch, the capture would occur at the trailing 3. Whereas if we look at the leading edge 8 launch and the capture happening on clock 2 at the trailing 9, that seems to be the most restrictive or the worst case combination. And so therefore, we actually have to look at that combination of launch and capture and make sure that the design actually meets the timing or the setup check for that particular most restrictive capture and launch combination. The hold check is a little more complicated. We have to understand that whatever edge is actually launching the data, if the next edge is not launching the data again before the previous one is saved, then you're okay. So meaning if you launch at 0 and at the trailing edge of 3, if the data has not completed saving into the flop 2, then basically you don't want the new launch at 4 to give you new data, and therefore you just want it to wait until the data is safely stored. So now if we look at the launch 4 and the trailing edge at T3 is actually still hasn't completed saving, then that is necessarily the most restrictive edge, and therefore the hold requirement is actually done at T3 for the hold check. So therefore, if we look at the most restrictive launch to capture, it's 4 and 3. And so if the data is actually safely stored, then you're okay. Otherwise, you're failing the hold check. So phase shift is a concept that is frequently used to report different launch and capture edges in the tools. It makes it easier for recording the data in the form of a timing report. Now, you can actually also have phase shift when there is a difference in phase between the launch and capture edges. Now that is because of the waveform of the clock has shifted a little bit at the capture clock. So it's possible that you're using a positive edge clock on one end and a negative edge clock on the other end. So therefore you're actually pretending that there is a shift in the clock itself. And so therefore you use the negative clock in one case and the positive clock in the other case. So all of those scenarios can actually cause different clocks for launch and different clocks for capture. In either case, in order to actually accurately depict what is happening in the tool, we can actually use a value of phase shift to transfer the data between launch clock and capture clock. Now, in the case of reporting, some tools just report what edge is launching and what edge is capturing and report that there is no phase shift. But some tools actually use phase shift and then on top of that report a clock period if necessary for the capture clock and the launch clocks. So if we look at this example here, we have data actually being launched on the launch edge and data captured at the capture edge. And because it's the same clock, launch and capture, we have a phase shift of 1 clock period. In some tools or in other tools, there is no phase shift and we just report 1 clock period. So let's look at where phase shift actually helps is when you have a multiple clock scenario. For multiple clocks, we need to understand phase shift and the basics of phase shift. So with certain assumptions, we can actually make multiple clock analysis really easy, which is to either use what clock is launching the data and what clock is triggering and capturing the data, or we could also use phase shift. It's easier to represent things in launch and capture data, but phase shift makes your timing reports much cleaner and easier to read. So with the phase shift, let's look at how it works. So timing analysis always starts at time zero. So basically, we are pretending that the worst case scenario actually always happens in the very first clock cycle. So in that case, even though the most restrictive edges happen at different times, we are bringing that most restrictive edge scenario into the first cycle when you use phase shift. So phase shift is basically just the delay adjustment that is used so that the first clock edges represent the most restrictive timing edges. So it's also based on ideal clock edges and not on the real signal edges. So there is no need for rise time and fall time and all of that other stuff. For setup or late phase shift, we have to unroll the ideal clocks, try to find out what the most restrictive non-zero delta is, and then just know that the capture edge occurs after the launch edge. Whereas with the hold, the same unrolling happens, and we try to figure out what the most restrictive non-zero delta is. But remember that the capture edge happens before or equal to the launch edge. In order to easily determine phase shift, we've come up with a simple equation which works for all scenarios, late, early, setup, hold, anything. And the way it works is you figure out what the actual capture edge and launch edge are, which are the most restrictive ones, and then figure out what the first capture and launch edge are in your first cycle and what they might be like. And so therefore, once you know those four values, you just plug it into the equation CE minus LE minus C1 minus L1, and this would give you your phase shift value. Let's look at an example of phase shift calculation for setup in a multiple clock domain scenario. So if we unroll a 4 nanosecond clock and a 3 nanosecond clock, basically the LCM or LCD is 12, and your most restrictive non-zero delta would be at 9 capture and 8 launch. And this is for a launch with the rising edge and capture at the falling edge or leading edge, trailing edge. So therefore, we are looking at ideal clocks here. So it's always leading is aligning to leading. And even though it's a negative edge triggered flop, what we are doing instead is we are actually reversing the phase of clock 2 so that the leading edges align. And so therefore, now what we do is we just try to figure out what is the launch and the capture based on ideal clocks. So in the case of ideal clocks, the launch edge, which is the most restrictive, is 8, and the trailing edge is the most restrictive capture edge. And in the cycle 1, launch edge 0 and trailing edge 3 is the capture edge. So therefore, you actually can now pretend that this same scenario is actually happening in cycle 1 and just kind of move the whole waveform to the left so that the leading edges align again, and so therefore that amount of movement that you see is the phase shift, so that the leading edges so that the same scenario happens in the first clock cycle is what is the phase shift. So if we look at the phase shift calculation, 9 minus 8, that is the CE minus LE, minus 3 minus 0, which is the C1 minus L1, and the value is minus 2. And so basically you're moving the waveform a little to the left by 2 units, so as to make it so that the worst case scenario is actually happening in the first clock cycle itself. So this is the phase shift for setup. We'll use the same clocks of 4 and 3 for the hold example, and in this case the most restrictive non-zero delta is again 4 launch and 3 capture, and so therefore you have capture minus launch, 3 minus 4, which is the capture edge minus launch edge, and minus 3 is where the capture is happening for a launch edge of 0, so minus 3 minus 0 for the first clock cycle, and so therefore your phase shift is minus 4, and that value is what is plugged into your timing reports for hold. Try this activity to improve your understanding.